Welcome back everyone. In this video we're going to talk about Newton's law of universal gravitation. And so it's important to understand that prior to Newton, people didn't really have a good idea of what was behind the planet's motion. Their motion was described fairly accurately. There were some good measurements that were taken, and we'll talk more about that when we discuss Kepler a bit later on. But no one really had a good mechanism for how the planets actually went around the sun. That is until Newton came along, and the story goes that he was sitting underneath a tree when an apple fell on his head. And that may or may not be the story, but as legend has it, he then looked up at the moon and realized that the same thing that was causing the moon to go around the Earth was responsible for the apple falling on his head. And we'll find out a little bit later on that you can actually calculate the centripetal acceleration of the moon. And because the moon is 60 times further away from Earth than an apple on Earth is, the centripetal acceleration is 1 over 60 squared times little g. And that's just something that we'll come back to. We'll put that in kind of a little thought that Newton had. But what Newton said is that there is a force of gravity between any two objects in the universe. And he said that it is proportional to how much mass each object has, and inversely proportional to the square of the distance between the two objects. Now this was as far as he was able to get. In order to turn this into an equation, you need a constant, and we call that the universal gravitational constant, big G. Now don't confuse big G with little g, 9.8, okay? Little g, 9.8 meters per second squared, is an acceleration. That's an acceleration due to gravity. Big G, on the other hand, is the universal, meaning everywhere, gravitational constant. It's probably clear to you that if you go to a different planet, G will not be 9.8. That's something that's particular to Earth, and we'll see why that is a bit later on. It's probably also clear to you that we're talking about an acceleration due to gravity because of little g being 9.8. But the universal gravitational constant is exactly what it sounds like. It's a constant which makes these two sides of the equation equal to each other, because on one side we have a force in newtons, and on the other we have kilograms times kilograms over meters squared. So if you think back to the very first unit, we need some units for g, which makes this cancel out. So therefore g has to have units of newtons and meters squared over kilograms squared. Now the value for g wasn't something that was discovered until many decades after Newton lived and died, and it was discovered by a scientist by the name of Cavendish, who did a very fancy experiment. He actually, if I do a little top view, he actually set up kind of a wire, and on the ends of the wires he put metal spheres, and then he put another set of metal spheres, and he could actually measure the rotation of the wire as these spheres were attracted to each other because of the law of gravity. And so Cavendish was actually able to measure the gravitational constant, which is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now this is not something that you need to memorize, but something you should pay very close attention to is that it's very small. And this has great importance for when we study other forces a little bit later on. So for now, the important thing is to realize that this law of gravity depends on the masses of the two objects and that it's inversely proportional to the distance squared. And I should also point out that when I say distance, I'm talking about a so-called center to center distance. For example, if we wanted to find the force of gravity between the Sun and the Earth, we would go from the center of the Sun to the center of the Earth. Now, because the distance between them is something like 150 million kilometers, the actual size of the planet, for example, Earth has a radius of 6,400 kilometers. It doesn't really matter the size of the Earth. It acts just like a point. But if we start talking about real life objects, maybe a 5 kilogram mass with a radius of 1 meter and a 3 kilogram mass with a radius of 1.5 meters, then you can't just take the distance between them. If it's 2 meters, you'd have to say that r is actually 4.5. So you want to do the center to center distance. Okay, so more on how to use this equation in the next video.